Wonderful.
Thank you. Let me just do so in a moment.
All right. Good morning and welcome, everybody. My name is Wangari. I am the lead research mentor at Aila Africa Journal Club. Our space promotes lifelong learning and develops research leaders. This morning, I was actually reflecting on a question on the kind of work we do and the impact we have had over the years since 2018 when we began the Journal Club. And this is the question that I came up with, which is a koan. A koan is an ongoing question that we can keep in our minds. How can we use informal learning to promote skill building for knowledge co-generation in our communities? So I'll repeat the question that I was reflecting on this morning. How can we use informal learning to develop skills for knowledge co-generation in our communities? So a lot of our work is based on informal learning, and I would now like to introduce all of you who are here. I will not have time to read all your names, but I see that you're already introducing yourselves in the chat. So I see Ahmed Abi saying he has a Master of Science. He's studying Master of Science in Animal Production. Research interest is zoonotic diseases that affect animal production and their marketing in Gulu University, Uganda. Wow, welcome, Ahmed. And then, of course, Daktari, who is our presenter, Dr. Fredrick Aila. He's from Maseno University, Kenya. He's interested in marketing, in particular agricultural marketing. We have Charles Ndede, PhD student, JQuat. His interest is fluid mechanics. Fatima Ali, very happy to be here. Fatsuma Ali Mohammed from University of Maiduguri, Nigeria, interested in gender and agriculture. That's amazing. Thank you, Fatima, for being here. It must be quite early in Nigeria. It's 9 a.m. in Kenya, so it must be 7 a.m. over there. We also have Tijani Pau, yeah, from School of Public Health, PhD candidate at University of Port Harcourt, Nigeria. Research interest is health system strengthening. Then we have Caroline Ambogo, who works at agrochemical food company. Please, if you're not muted, please mute your audio. Caroline's interest is in marketing communication. Wow. Isaac Kataka from Park University, that's Kenya. PhD candidate in organizational leadership. His interest is effective leadership in the church. Then we have Sahid Odwola from Obafemi Awolowo University, Ile-Ife, Nigeria. Carolina Ambogo from Maseno University, Kenya, PhD candidate. Feel free to tell us in what field, Caroline, if you don't mind. So keep introducing yourselves in the chat. And now, in the interest of time, I would now like to hand over the session to our facilitator. Please note your questions meanwhile and your comments in the chat. And we will be addressing them when we enter plenary, where we will actually field a few questions. These sessions go very fast, so please let's make it interactive in the chat. And David, thank you for hosting us. David is our knowledge manager at Aila Africa. Kindly make Dr. Aila a co-host to enable him to share screen. Thanks, David. We still have more people coming in, so keep introducing yourselves in the chat. And now I would like to introduce Dr. Onyango. Karibu.
Thank you, Joyce. We had already interacted with David early in the morning. And so I think my screen is shared. Is it shared?
Yes, thank you so much.
Thank you.
Wonderful, okay.
Yes, so thank you, Joyce, for such a warm welcome and an introduction this morning. First, I want to indicate I'm glad that my student, Patricia, was able to connect me with you. And then we had a chat in last week and early this week with Aurelia, your executive director. And here we are today. I should have been teaching my class, so I invited my students to join this session. I'm expecting a number of them to come on board. so that we can learn together. And after this, we can go to our normal class. Again, it's also distributed because of COVID-19. Welcome, colleagues. Let's journey together this morning as we reflect on quantitative data analysis, and in particular, regression analysis. So I will proceed. Because of issues of bandwidth, I will now stop my video. Good. So then I will now indicate my formal title and what I have read. I was at the University of Nairobi. I graduated in 1999 with a BCom degree, marketing option. Proceeded to work with Coca-Cola for 10 years. At that time, I got my MBA at Maseno University, and then a PhD in 2014, Maseno University. I'm a member of the Marketing Society of Kenya and a Kenya Institute of Management. A senior lecturer in the Department of Business Administration, as well as director self-sponsored program. Now, just a brief on my university, that's Maseno University. This is the only university that is astride the equator globally. I wish to invite many of our colleagues from portions of the world in Africa, and even those in Kenya, to come and visit and experience what we take for granted being on the equator. It's a premier university for citizen digital literacy. All our undergraduate programs are offered with information technology, and we are transforming ourselves to be a strong university in research with a robust and pragmatic faculty. And I'm inviting you to engage us. We have a large student base, and in the recent selection by CUPS, that is Kenya Universities and Colleges Central Placement Services, we were ranked second by student choice in the country, in excess of 6,600 students and a strong postgraduate training base. We also have a vibrant e-campus. Now, just a bit on my research interests and publications. Later on, when I share this with Aid Africa, it can be made available. I have many students that are ongoing in their work, and that forms part of my research interest, but also those that are driven by myself, especially in agriculture, as well as what the university is doing. I'm engaged in several ongoing projects, and I like the question that Joyce has raised about informal learning to develop skills for knowledge co-generation. Joyce, I want to respond that yes, I'm engaged in an EU-funded project, and we are looking at transdisciplinary research, and particularly using multi-actor communities of practice. And this involves going to the ground to engage with farmer bases, with value chain actors, and to glean and generate information from them, but in the process to co-generate knowledge, co-construct knowledge, and see how we can translate this into policy dialogues across the spectrum. I'm also interested in mentorship. So when I was called up to engage, I felt this was a good opportunity. I have several publications that can be scrutinized and probably see what I've been able to do with others. And so here I display my ongoing researches. The first one is funded by the Fredrick in the US. It's on sustainable development for HIV health fellowship. And so my interest is on mentoring those in agricultural sector on food security related issues. And one other research that's ongoing is a global food security challenge. It's a grant that will end next year. And the EU project is termed upscale, that is upscaling the benefits of push-pull technology for sustainable agricultural intensification in East Africa. It comprises a North-South consortia with universities and other players. We're operating in 5 East African, sorry, in 5 East African countries, that is Kenya, Uganda, Tanzania, Rwanda, and Ethiopia. And we're doing a small consultancy for FAO, that is Food and Agriculture Organization of the United Nations, which is ending end of this month, on how to engage youth in agriculture. And then, of course, earlier on, this was a USAID project that was operated by Windrock International on poultry feed formulation and production cost improvements. Now that we are here, we can reflect on a couple of issues on data analysis. And thank you for joining so that we can level our expectations together. I'll be expecting you to indicate on the chart your expectations, and during the plenary, we can reflect on them, whether those expectations have been met. We'll be looking at an overview of regression analysis, a bit of simple regression analysis, multiple regression analysis, and I'll use my example to show you certain things on models of qualitative choice. And so let's begin. I have posted these questions here, and I'll linger on this slide for a moment. You can take a snapshot and probably using the chat, try to respond to some of these. I do not intend to answer the questions myself, but I think we can reflect on it as we go along. So some of the questions are, what is regression analysis? When can we use it? What types of questions does it answer? What data types are suitable? How do we prepare the data? And how do we proceed? So as you reflect, we hope that I may answer some of these questions, but as we interact, and as Joyce had already pointed, we can co-generate knowledge and find responses to these questions. So let's then reflect on the overview of regression analysis. I wish to note that we usually would want to use regression analysis when certain conditions are suitable. And top on the cards is when we believe that we can identify and quantify some functional relationship between two or more variables. The crux is believability. Are we able to identify? Because this is under quantitative paradigm, and so the categories must be identified and isolated beforehand. And for us to fit these functional relationships, there must be some time difference, some temporal difference between the action and the outcome thereof. And so regression analysis takes the general form, which is read as y is a function of x, where x is the regressor and y is the regressand. And so when we think of simple and multiple regression, in simple regression, generally, we only have one independent variable, and we can think of it as bivariate regression. But in the multiple regression, we tend to have more than one independent variable, and we can think of it as multiple regression. And it takes the form of equation 1.2, which is read as y is a function of x sub 1, x sub 2, x sub 3, all the way to x sub k, for all values of I ranging from 1 to k. And we see that all these variables are independent and are used to explain the outcome variable, which is y. So the simple straight line equation is the starting point as depicted in equation 1.3. And we note that this equation can be transformed into a linear model for the population, which we read as y is equal to beta naught plus beta y xi plus the error term. Now, this model, that is equation 1.4, has two components. It has the deterministic portion, which basically is beta naught plus beta ixi, and the random error term, which is read as, which is a Greek epsilon. And we realize that two elements take place in this model, the deterministic and the random component. Now, beta naught and beta xi are unknown, and we're interested in estimating that in the sample data, because this is the population model. So then I show you the sample data equation, the linear model on sample using sample data, which is equation 1.5. Y is equal to b naught plus bi xi plus the error term, which is now depicted as E. So the error term is a random error, and it is the residual. We note that b naught and b sub naught sub I are the estimates of beta naught and beta sub I, respectively. Now, equation 1.6 is the estimated regression model. And I want to point here that occasionally I read theses of students, and there's an issue, because when we estimate the model, we cannot retain y as depicted in equation 1.5. We have to show that we are now estimating. And so that way we use y hat. We give the hat there to indicate that we have estimated this model. And then b sub naught is the intercept, and b sub I is the slope of the estimated regression model. Now, there are several options for estimating the model.
Daktari, I am
Yes.
following, and these are really good questions where we have begun. So far, we're going well. Okay. I was just wondering, for the interest of those people who may not even know what regression, where it fits in research, maybe you can also, I don't know how the slides are coming along, but you can also give us a concrete example, which is more situated in in a question, and we'll be able to get with a very more concrete example. I like the explanation so far, and the slides are very clear. So perhaps you could also give us a scenario. And I know maybe you're planning to do that coming up. And so I'm just getting that request from some members. I think we are all in different levels, and that's the beauty of our space. We have people who are just beginning research, and people who are literally retiring. And so we have all kinds of different fields of study as well. Thank you.
Okay. There are several examples that can be alluded so that we see. Let's take one now that I saw a number of people are in marketing, agriculture, related fields. A typical example would be maybe using sales as an outcome variable, and several factors may be used to explain sales. One of them might be advertising, for instance. And so if let me go back to the first slide, sorry. So let's take this slide. Y is a function of X. And so Y will be sales, and X will be advertising. Generally, from a business purview, we use advertising to display and to let our population, or rather our customers, know our existence. And we hope that when they see an ad, they will respond. A good example is the call up for this meeting today. I know that Aurelia, working with your team, prepared, having engaged me, prepared the advert. And then the advert was a banner ad. It was displayed within your networks and within my networks. And with that display, then there's a response. And the response is the 94 people who are connected to this webinar this morning. So how do these two work? There will be the action that you took by displaying that there will be a webinar on Saturday morning, and then there'll be the interest it creates on the recipients, and then we can now see that we have 94 people have responded. So the response variable will be the number of people who have come, and the independent variable or the explanatory variable will be the advertisement. And so maybe we'll measure it in terms of in how many fora was it displayed, and in each fora, how many people were involved. And so if one forum has, say, 1,000 people, then we'll say, yes, 1,000 people have seen it. And then maybe out of the 1,000, so many have come to this webinar. Joyce, does that give us an example that we can work with?
No, thank you so much. I mean, I'm in psychology, I'm in social sciences, but I'm getting you're now talking about two variables. And I think that is a really good example. And that brings the entire regression in picture. I think some people are missing the bigger picture because they were encountering this for the first time. So that's clear. Thank you.
Good. So I can proceed.
Yes, please proceed. And members, if you have a question, feel free to type in the chat. We will get to Q&A at the end. So at any time, if you have any kind of question, feel free. We like to make our sessions interactive because we already know you can Google this online, but that's the reason why we are all on the Zoom call today. Thank you.
Okay. So I was at the estimating the line of best fit. I've displayed ordinary least squares, but there are alternatives that maybe I've not brought up to this chart. One of them is the method of moments, and that you can find in the text by Madala, and then the method of maximum likelihood. But for today, we will reflect on the ordinary least squares, and I'll be giving an opportunity for us to do some arithmetics. So I hope we have our pen and our calculator somewhat to do some simple arithmetics. So then.
Okay, thank you so much. And somebody asks here, and I don't know how we can do the questions. Do we do them as we go along? Because there's a question in the chat.
Okay.
Somebody's saying, Daktari, please clarify what you mean by functional relationship and linear model. So Modoni is asking that. Okay. And then Linaus is asking, I hope I pronounced the name well, Linaus. He says, my concern would be how to introduce moderating and mediating variable in regression equation. So now those are the two questions so far as we go along.
Okay, let me see what I cannot do now. We can open it up for the plenary at the next time, next season. So
okay,
the functional relationship is really, okay. We come back to this. I think this is introducing many interesting things. We must have some theoretical purview that one item may be connected to or related to the other. Like the example I gave, the advert, I think Aida Africa felt that when they place an advert, it will produce a response. So there's some connection that might exist between placing the advert and the response for people to attend the webinar. So that's a functional relationship. And at this point, we are saying it's a functional relationship because when you unpack the entirety of regression models, that function may take various forms. And so the next question is linear model. So we are, in this case, proposing that the functional relationship is that of a linear model. And that's why equation 1.3 uses the formula of a straight line. And so basically what we're doing is that we are drawing this from mathematics. They've already established that a straight line will have the equation y is equal to B naught plus B sub 1 x1. And it can be showed in various ways. Y is equal to A plus BX. That is the one that we used to teach in high school or as we start our training at the university. So basically, in the simple linear regression, we are presuming that it will follow a straight line. I did not show any scatter plots, but if you have a Cartesian plane, your X and Y, and you have all the responses, the people who come in, say for this webinar, and you plot them, they will be clustered. And in that cluster, we might easily logically try to fit a trend line connecting them. Say, if we asked ourselves, the webinar started at 9 and time is progressing, how many people are joining, how many people are leaving? We can try to plot that, but that's for another day. Now, the issue of mediating and moderating, I did not prepare for this, but the crux is when we have multiple regression, then it's possible to think of now moderation and mediation. In a multiple regression, we have more than cases. We have more than one independent variable. Like in equation 1.2, we have x1, x2, x3, up to xk. Now, in a moderation situation, we may theoretically propose that there is a variable, say we can call it x3. X3 might be a variable that, though when fitted in the direct relationship with with y, may give us some results, but when it interacts, say, with one of these variables, it produces results that are a bit more robust, improves the explanatory power and the like. So in that case, we're thinking of a variable that when it interacts with the independent variable, it produces a more robust outcome. A good example would be in our example of the advert for this webinar and the response. Now, there's people who know me, classmates, college mates, students. They are probably in this webinar today because they know me. So knowing the facilitator might be a confounding factor, and it might be causing an interaction for the adoption, or rather the joining with the webinar. In such a case, then probably, I don't know whether it works, knowing me as could be a variable to be included, and it may produce that outcome. Now, when we think of mediation, basically we're thinking of an alternative path. So in our number line, the direct path will be to try and show that x1, x2, x3 have a direct relationship with y. But what if there's an alternative variable that is slightly out of the spec, and it gives us an alternative pathway to reach the outcome variable? So then we can think of mediation. Good. Does that sound like it can help?
Yes, I really like that you're giving us examples. And so I can still see a few more questions in the chat, but as you said, we keep monitoring whether they can be answered at the end or as we continue.
Thank you.
Ruth Odhiambo is asking, may I ask, is it a must to have a moderating or intervening variable when using regression models? And then I also had you mention earlier the word ordinary least squares. So you can please tell us what that means. Okay. Thank you.
It's not a must to have moderating and mediating variables. Well, of course, for universities, it might be some tradition. When I read my master's and my PhD, I came to learn about moderation and mediation at my PhD, apparently. but I didn't use it. So it's not a must. And I've seen many other students who have not used them. In fact, for my university, our feeling is that probably we need to explore other options in regression analysis. So in a sense, we may not necessarily have everybody use mediation or moderation. They sound lofty, but they usually are latent variables that are not observed directly. And the problem is sometimes they do not have huge explanatory power. And so it just fits in well for the academic paper, but may not have a strong external validity in terms of value, especially when you use primary data. Now, let's look at ordinary least squares. Here, we're interested in the line of best fit. Remember, in our equation, we're trying to fit a trend line connecting all the values. And if it's a straight line, it may not connect all values. And so when you think of ordinary least squares, we're looking for the line that will minimize the deviations from all those values that are clustered within our response. So probably I would show one or two things here, and then you see from an arithmetic point of view. Equation 1.7 shows that the error is equal to the difference between the actual value and the estimated value of y. In other words, the trend, the line that we draw connecting values will be our estimation. That's why it's an estimate. And y is actual observation. So the least squares, ordinary least squares basically try to minimize the squares of those deviations. So we can say that if actual values of y, that is yi is greater than our estimate, then y is greater than y hat I. And so the error will be positive, and the converse is true. Our interest is to produce a line that would make these errors to be zero. And so the summation of yi minus y hat I is equal to zero. So that's the sense of ordinary least squares. And so we can show here that ordinary least squares tries to minimize the sum of squared errors. It produces a line that the sum of the squared errors is less than it would be with any other line. And so equation 1.8 shows that we want to minimize the squared errors. And that's why we say that the summation of yi minus y hat I, when we square that summation, it must be minimized. That's why it's least squares, ordinary least squares. So I hope that helps to explain the other question that was raised. And so we are thinking of determining the line of best fit. Really, that's the essence of using OLS. Is there a line that best fits the variables that we have observed? And so what I am doing next is to try and execute one example. And so probably we can have our calculators ready. You can use your phone. Most phones have calculators, but if you're using it to connect, probably your arithmetics can help you. You can use longhand. So for us to fit that line, we will need to use sum of squares and cross products. And we'll show an example so that you can compute. Now, this is just arithmetics, the sum of squares of x. In other words, we'll sum all the squares of x, and then the sum of squares of y, we'll sum all the squares of y, and the cross product of x and y. Probably a table will show us. Let me move to this table. It's a bit familiar because we are now using sales and advertising. So let's make this assumption in the worked example. Assume that Sadila Enterprises monthly activity for the first 5 months of 2021 is given by this table. So we have month 1 to 5 and then sales in Kenya shillings from 450 to the last one, 420, and advertising expenditure, that is 50 to 45 on page 16. So our quest is to estimate the regression equation. And so this example probably answers the question that was raised earlier as a typical scenario for using regression. So we may need to do some computations so that we are able to find some response. So on this table, what I've done is to bring the information in the previous table and then added what is necessary for us to compute our regression. We have the observations, we have advertising, and then we have sales. I've rearranged this so that we see that advertising is the explanatory variable and it is producing a response which is sales. In other words, there may be other factors that influence sales, but we have singled one, which is advertising in this scenario. And so we will need to compute for each observation the summation of X and Y, the product of X and Y. So basically for the first month, it will mean 50 multiplied by 450. And then the summation of X squared will be seen in terms of 50 squared, and then summation of Y squared will be 450 squared. And each column is added so that it indicates your total. At the bottom, we'll have a total for this, and then probably I already did that earlier. So it produces values as depicted on page 18. So you can say that 50 squared is 22,500, sorry, is 2,500, and 450 squared is 220,500. These are values in Kenya shillings. You may want to translate it to other currencies to see what it means. You should have known better to use dollars probably. The totals will tell us values, and we'll use this table to compute the regression equation in a moment. Now, on page 19, I've done some working, and it's straightforward. We can use our...
Yeah, Terry, I'm still monitoring the charts and people are following, and some questions are more general, but there is one specific one I see that might be on what you are speaking about now.
Okay.
Esdras Obosol says, I can see that you have up to 8 equations for simple regression. My question is practically, how many equations do I draw when reporting the thesis or research paper? So I'm seeing in the chat quite a number of more general questions. So I guess more people are asking about the bigger picture, and today's session is going into some specific equations. So maybe you can advise whether that will be a question you'll address later.
So the question is, you can repeat how many questions? How many equations?
Yes, how many equations for simple regression?
Now for simple regression, basically, from ordinary least squares, we're looking for one line that has the best fit. So it will be a single equation. But for your research paper, that will depend on your objective. Did you envisage a simple regression equation, 2 variables in play? One is an outcome and the other one is an explanatory variable. So then you will fit that. But my caveat is that more often than not in social sciences, we tend to have many factors that are in play. For instance, the example we given here, we are showing advertising and sales, but there could be other factors, and that's why we think of multiple regression. We could be having salespeople's effort, we could be having the reputation of the company, we could be having the locality or loyalty of the customers. And so these are questions that can be explored in our various disciplines. Somebody from human resource management might want to see the way we administer our compensation plan, for instance. And probably somebody from a rights-based organization may be interested in whether it's fair trade. Are we using child labor, for instance? Are we exploiting our employees and the like? So there may be many factors. But when you're thinking of a linear regression, for that question in mind, we are looking for one line that best fits it. But when we think of moderation and mediation, we may have other lines that we are fitting to see whether our theory is sound or otherwise. So back to question 9, page 19. Basically, what we have done is to transpose the information from the table to fit in, and probably working through, we have the sum of squares, the squared sum of x is 370, the squared sum of y is 1680, and the summation of x and y's, the sum squared of x and y's product is 2410. From the equation, we have produced the slope is b1, which is equal to 6.151, and the intercept is 125.81. So the estimated regression equation is given as y hat I is equal to 125, the intercept, 0.1881, plus the slope, which is 6.51 xi. And we note that this is in cells in Kenya shillings. So what we're trying to say in a nutshell, that for 0 shilling spending on advertising for Sadila, for the range of the 5 months, there will be an automatic sales value of 125,810. What I've done is that because they were Kenya shillings thousands, I have multiplied 125.81 by 1,000 shillings. So in other words, the intercept there tells us that the business has produced some value that is not explained directly by advertising. Yeah, maybe it's reputation, its location, and the like. And now next, we're saying that we can use this equation to make a prediction. The crux of the prediction is that it has to be within the range of the original data set. So I've asked the question, if xi is equal to 60, then what is the value of the estimated sales for that period? And working that, we find the estimated sales will be 516,410. What we're saying here is that we can only, let me go back to this, we can only use the equation we produced to predict values within the ranges of values within the original data set. So the lowest advertising expenditure is 40 and the highest is 65. We cannot propose, for instance, to estimate sales at 35 or, sorry, yeah, when advertising is 35 or when advertising is 70. Do you know why? We have only estimated this on the basis of the range of the data, because beyond the data set, the minimum and the maximum, this model may not be a linear model. It may be curvilinear. Many other things might be happening. And so the caveat is that we only can estimate within the range of the data set. This luckily can be done using software, computer software. I do not know whether I've exhausted the software. Truly have not. We have SPSS that is common among students, but R is equally good, and it is GNU, Starter, Minitab, eViews, and many others that you can think of. So up to that point, any question? As I drink water.
Yes. Thank you so much, Dr. Quite a number of questions, and this is a very well attended webinar. High numbers. We've wanted to learn this for a long time in the group. People keep asking, and there are, as I said, more general questions. Okay. And there are also some specific questions. So I think the general questions will be at the end. So Mike asks, do we assume the slope starts at 0? Can it pass through the X or Y axis? And a few people are asking for the presentation. And then we have other more general questions also in the chat. So this one is from Mike.
Okay. I can indicate about the presentation. Yes, I think I will share with your team to be circulated. I'll be glad to do that. And then again, the charts, once they are, once you produce them, we can engage with colleagues even beyond this webinar. And we can invite, I hope you have a forum where people can engage, and so we can.
Yes, thank you so much that you will share the content. Yes, we have a platform and I've shared the links for those who would like the recording. So, okay. Yes. So Mike had asked about the
slope.
Yeah, the slope.
Yes, it doesn't necessarily have to pass through the origin. Even in our worked example, sorry, I didn't have any diagrams to demonstrate this, but you see the intercept is 125.81, as you can see on page 19 of my slides. The column in the middle with red, the intercept is B0, and it is 125. It means for the example we have worked on.
Kindly mute yourself if you're not speaking. All right. Please proceed, Dr.
Okay, so for our example, the intercept does not pass through the origin. So I think you can mute the participant.
Yes, so and if you do not have your real name, please rename yourself kindly. Thank you. Oppo A53, this is the last warning. Please rename your Zoom name. We will not have you here if you do not have your real name on Zoom. Okay, thank you, Dr. Please proceed.
Okay, so I'm asking Mike to see that the estimated model is 125 for beta naught, which is the intercept. So basically, we can explain this that for Sadila enterprises, for the observed period of time, their slope is not starting from 0. And generally, slope starting from 0 will mean for a business that they are starting, and probably they have not launched themselves. And if you do some trial sales before you launch your product, you'll have some value of sales before time 0. And so it does not necessarily have to start at 0. Thank you. So then let's look at the assumptions of the linear regression model. I have indicated 4 here, but generally when we move to the multiple regression, we'll increase those assumptions. So the first one is that the error term is normally distributed, is a normally distributed random variable. And there is equal variance for all the y values. And we must then assume that it is linear. So there's linearity. If we find that it is not linear, then that assumption is violated. And so we may need to fit an alternative. And then the fourth one is that the error terms are independent of each other. Because if they're not independent of each other, there's a likelihood of autocorrelation. So I want to just delve into the issues of independence of the error term. We note that there is autocorrelation when the error terms themselves are not independent, then they will interact, and that will produce a problem for our regression, our estimation will not be sound. And we usually use Durbin-Watson statistic to test autocorrelation, as it's presented here by equation 1.14. We set the hypothesis that for the correlation of the population correlation, or rather for the successive errors, that there is no autocorrelation existing. And the alternative is that autocorrelation existing. And so our interest is to rule out autocorrelation, because if you don't rule out autocorrelation, then we'll be producing spurious results, and we cannot use any predictive value of a regression equation that we estimate. And so we may want to check for goodness of fit. What is the standard error of estimate of our equation? And there are usually two elements of interest fitting in the standard, the standard error of estimate and the coefficient of determination. Now, the coefficient of determination is the squared correlation of the entire data set of population. So equation 1.15 shows us the standard error of estimate, and it is a square root of the sum squared of the deviations that we have observed divided by the degrees of freedom. Now, the degrees of freedom here for a simple equation, simple regression equation, is usually n minus 2. And we are noting that the variance of the errors should be the same throughout, but the variance is not known. And so we have to estimate this on using sample data. And I will be showing the mean square error to help us estimate the standard error of estimate. So equation 1.16 now helps us to show the sum of squared errors, which is the summation of the sum of squared of y less the quotient. The quotient is the sum of squared of the product of x and y. We square them and then divide by the sum of squares of x. And in our case, we have we have n minus 2 degrees of freedom, where n is the sample size and 2, basically we are taking away the two elements, that is the two estimated elements, the parameters b naught and b sub I. And so equation 1.17 will be relevant for us in the next estimation. MSE is equal to SSE divided by n minus 2. So I proceed.
Wonderful. And I like that you are just about to give us a worked example. That's what one person is asking in the chat, Ahmed Abdi. So yeah, wonderful. Please proceed.
Thank you. So I'm asking us to recall the information we already gathered earlier on, and I can just display them back in a short while. Yes, so this is the information that we have worked on, and some of the values, if you picked SSX is 370, SSY is 080, SSXY is 2410. And remember that the intercept is 125.81 and the slope is 6.51. Sorry, I am pushing you hard to remember many things. My colleagues in psychology will tell you we only can remember so much. So based on our argument, we can transform this information and work. And so I have done so in slide 27. So the sum of the sum of squared errors has been computed to be 382.43. The mean squared errors is 127.48, and the standard error of estimate is 11.29. So we're noting here that the standard error is expressed in the same units as the dependent variable, which in our case is Kenya shillings 1,000. So basically, the standard error of estimate measures the variability of the Y values around the fitted regression line. So basically, it helps us to see the dispersion of the Y values around the mean, given the specific X value. And then we need to introduce correlation analysis at this point. And you remember, correlations will take values ranging from -1 to +1. I must say that a couple of years ago, a student appeared in a defense and had perfect unity for some of his values. Unfortunately, he could not pass because that was outrageous. Because you see, everything, I mean, in real life, having perfect unity may mean that probably there was no isolation of the variables being measured, but that's for another day. So basically, when you have -1, it means that we have a perfect negative relationship between the two values of interest. And equation 1.19 may be relevant for us because it helps us to see the sum of the total deviations, which is abbreviated as SST. Basically, we're looking at the deviations, and now I think you're getting familiar with this notation. The deviations between yi and the estimated, sorry, the mean y of y. We square this, and so this equation exhibits two elements. One is what is observed or explained, and the other one which is not explained. So I will start proceeding by looking at the explained deviation. And the explained deviation is seen in the equation 1.20, which is the sum of squares of the regression. And we can abbreviate that as SSR. So basically, we are able to explain this, that the estimated deviations between the estimated value of y and the mean value of y. That gives us the sum of the squares of the regression, SSR. But the unexplained deviations will be the ones that we cannot observe directly. And so we'll be looking at the sum of squared errors, and that is shown in equation 1.21. And we can see the difference here is that we are having yi's less the estimated yi's, and we square the summation thereof. From this, we're able to show the correlation coefficient as equation 1.22, where r is equal to the square root of the explained variation divided by the total variations. And from our notation, we can say it's the square root of SSR divided by SST. So then R will provide a relative measure of our model's ability to explain the deviations of the Y values. So some computation can be done, and we're using equation 1.23 to help us, which is basically R is equal to the squared sums of the product of X and Y divided by the square root of the squared sums of X multiplied by the squared sums of Y. So from our example, we can show that our R is 0.988. Now, maybe I'll pose a question so that maybe somebody can unmute and engage. What is your opinion of this R? We have produced an R of 0.988. So probably Joyce, you can.
Yes, thank you for. Thank you for that question. So who would like to raise their hand? Kevin Akumo, welcome.
Thank you very much. What I can say about R, the value of R, Hello, can you hear me, please?
We are hearing.
Yes, we can hear you. Please proceed.
Okay, let me give it a try. I think R is amount of variability which in amount of variability in Y, which is accounted by the X or the independent variables.
Mm-hmm. So what's your comment on the value that we have produced? Remember, we have been working with some data from Sabila Enterprises, and we have produced an R of 0.988. So what's your opinion about it?
It's kind of there's a strong correlation.
Thank you. It is a strong correlation. So you've told us its strength, and the strength basically tells us about its magnitude. What else will you decipher from it?
Also have Agnes Sansa and then Titus Kitai.
Okay.
Agnes, welcome.
Well, I think if the value of R is, yes, I think if the value of R is 98%,
Mm-hmm.
I think that it means the model is highly significant and there is a very strong model fit between the variables.
Okay.
Wonderful. And that's the same thing as Janet Surum. She says the same strong positive correlation between X and Y. She's typing in the chat.
Okay.
Emmanuel Shikalipa agrees, strong positive correlation. Anes Kirui says 98.8% of variability in sales can be explained by advertisement. And then James Amenge agrees, positive, strong correlation. So I think we have that. Titus Kiptai, I think will be the last one. And then we proceed. Titus, welcome.
Okay, I don't know. It's a bit, thank you very much for that. For me, I feel like if it is 0.98 and we are looking at -1 being a significant, close to -1 being a significant, and close to positive not being very significant, I tend to be of different or opposite. The team is talking about strong significance, but my thinking is that it's low.
Okay, thank you for having a divergent opinion. So let's try and respond and see one or two things. I will go back to the place where I explained that. So I'm using Pearson's product moment correlation coefficient, and we're saying that the values range from 1 negative to 1 positive. I want to correct one notion. These values do not show significance. Significance will be seen by using a test statistic to confirm that at our cutoff, and many times in social sciences, we put a cutoff at an alpha of 0.05. Then we can confirm whether the regression, the correlation is statistically significant. But there are two things we can see from that response. So I've displayed this and I've dissuaded us from using the term significant because I don't think we have estimated to confirm that 0.988 is significant statistically. But we are saying that it is showing us the correlation between sales and advertising and sales. But the other question I want to raise, the other response I want to give is that the correlation coefficient will be telling us two things. One is the direction of the relationship. So because this is positive, we know that it is a positive relationship. And what we can see is that as we increase our investment or our expenditure in advertisement, there is a likelihood that sales will be increasing. When we reduce our spending on advertisement, sales is likely to reduce. That means they are going in the same direction. That's direction. The second thing we need to read from correlation coefficient is the magnitude of the relationship. The value here is 0.988, and I can agree with our colleagues who said it was a strong correlation. But then there's a problem there because a very strong correlation, and I'd hoped that colleagues would pick that. Let me show you why that strong correlation might be worrisome. And by showing you, I'll go to this slide. If you can see my table, one problem here is that we have very few observations. There are only 5. And we're using 5 for our computation for this class. In reality, we need many observations. The rule of the thumb is for us to fit regressions, we need a minimum of 30 observations. That's the rule of thumb. And so 5 is way below. And so some of the things we are seeing here may not be real. If we are to look at Sadila enterprises, we probably need to have observations spanning 30 months. And then we see the outcomes because you only have one dependent variable. But if you have many variables, then the rule of the thumb it calls for us to have much more observations. So probably we are having a very strong positive correlation coefficient because we have a small data set. I had hoped that colleagues will have pointed out that, but thank you for your feedback so far. The next one is coefficient of determination. And so I have displayed 2 equations, 1.24 and 1.25, to show us the coefficient of determination. Now, the coefficient of determination is usually used as a measure of goodness of fit of the model. It gives us the explanatory power of the model. And it's usually denoted as R squared or R raised to power 2. Now, we have 2 options to do so. One, which is the straightforward one, is what I have showed on the last line of page 32, which is basically R squared. You take the value of R, square it, and so you have it. But from our data set, we have variations on the computed value based on equation 1.25 and the actual value when we square R. One rationale for this might be the fact that we had rounded off some values. Maybe I can show you that so that you see that some of our values were rounded off. In our computation on this page, we rounded some values, and when the values are rounded, they'll have some impact. And so there's a differential in the 2 produced values here. But you can see there's a semblance. The R squared based on equation 1.25 is 0.971. And when we square the R value, that is 0.988, we get 0.976. So the difference is not so huge, but in real data, that can be worrisome occasionally. So what are the limitations of regression analysis? Let me point 1 or 2. One of them is that regression analysis cannot determine cause and effect relationships. We cannot here say that advertising causes sales. Those are 2 different worlds apart. What we are saying is that advertising is associated with sales. That is what we have been able to do. And so probably we are answering the question, when do we use regression analysis? And so I think that should be clear. And then the second one is that the regression model can only predict Y for the ranges of X in the original data set. If we introduce one more data point, that equation may not be sound. Why? Because we had made the assumption that this was a linear relationship. What if that value sets the equation out from that linearity assumption? And then lastly, we may need to check for spurious correlations. Sometimes we have values, we have things that are not theoretically sound, but when we fit them into the equation, they give us results. And so I would say that learners may need to just ask themselves, is there a theoretical soundness for the estimation that we are now making? I will now move to testing the parameters of the equation we have fitted. And one test is the test for beta I. We usually set the hypothesis, the null hypothesis, that beta naught is equal to 0. By setting that hypothesis, it may mean that if the beta naught is equal to 0, it means that it is not doing any work to help us in predicting the values of y. And so we use the student t statistic to test the regression, the population regression coefficient as produced by equation 1.26. Now it carries n-2 degrees of freedom, and we usually use the standard error of the sampling distribution of BI. So then we have worked out this in equation 1.27, where the standard error of the regression coefficient is given by the standard error of estimate divided by the square root of the sum of the squares of x. From our example, we find that the t-test produces 11.09. So I think we need to pay attention here, and I'm drawing your attention to using your t-distribution table. Most textbooks in statistics and econometrics will have these distribution tables at the tail end, but you can also produce them online. So if we set an alpha of 5%, that means that's the cutoff. So our alpha is 5%, and we can show the cutoff point in the table. It is plus, so just a bit. Our alpha is 5%, and we have 3 degrees of freedom. Remember, it's n-2. Our data set had 5 observations, and when you take away 2, you get 3. I read this straight from the t-distribution table, and I used the two-tailed test. The value of t is plus or minus 3.182. And so we need to make a decision. The question is, do we, what do we decide with our output? Remember, our output is t is equal to 11.09. So the decision rule is that do not reject if t test is between plus or negative 3.182. Reject otherwise. In our case, we reject the null hypothesis that B naught is equal to 0. Why? The t value that we have produced is 11.09. And so we can say confidently that at 5% level, a relationship seems to exist between sales and advertising. Anybody with a comment on our test?
So do we have some question specifically on the test? There are quite a number of questions on the chat, Daktari, and as I said earlier, it looks like you will need a series so that some of the more general questions can be addressed maybe in a different session. Today's session went down to the details, and this is what we were looking for. So I don't see any questions that are specific to the test that is on the screen, so you may proceed.
Thank you. Then the next issue is on the confidence interval for B sub I. In other words, now that we have produced a t-statistic for it, and we are confident that at 5% level of significance level, we note that at that level, B is not equal to 0. So then what's the range? What's the confidence interval in our case, we have set this at 95 level of confidence, and equation 1.28 might help us. And it shows us the ranges of the value of BI will be from 0.0017 to 13.01983. Now, I used 5 decimal points because at 2 decimal points, I was going to tell you from 0, 0, and that will be absurd. Now we can say that we can be 95% certain that the regression coefficient for the entire population of all values is somewhere between 0.0017, 0.0017 and 13.01983. Now this helps us to see the ranges of the values of B sub I for the population. Now, we may also want to test the population correlation, and that is usually given by rho. So this is read as rho. So we say that we set the hypothesis H naught rho is equal to 0 and the alternative. And so we use the test, see equation 1.29, that the t-test is equal to R, that is the regression coefficient, minus the population correlation, the correlation coefficient minus the population correlation coefficient divided by the standard error for R. And equation 1.230 gives us the standard error of the correlation coefficient. We have computed this for our values, and we can produce the student t-test, which is equal to 17.33. Now, if we set our alpha at 5% as the decision rule, we say that do not reject do not reject if t-test is between plus or minus 3.182. And because our t-test for the population correlation is 17.333, which is above 3.182, we reject the null hypothesis. The next item, probably before we reflect on other issues, is on the ANOVA table. And on this
wonderful
page,
thank you, Dr. I see that, yes, I see that we have about 12 minutes to the end of our session. And I think what I can say with the charts, if we don't reach to them, is that you'll be able to answer maybe later on email. We are saving the charts, so that will work, so that we can have maximum time learning from you. This has been wonderful. So I think you can proceed and tell me how we can do that.
Yes, what I want to do, what I want to do is, after displaying this ANOVA, then some small worked example.
Okay.
Then we can open it up for discussion.
Wonderful.
Then probably as indicated, we can look for another occasion to think of other regression equations. Is that agreeable?
Yes, that's agreeable. Please proceed.
Thank you. So then we need to produce an ANOVA table, which is analysis of variance. That's ANOVA. And in most software, we usually find a display, and the display is usually, this is what has been extracted from that display. It usually has the source of variation, the sum of squares, the degrees of freedom, the mean square, and the F ratio. And so basically what we are showing here is that these values for many of us are usually computed by the software, but this is what it actually means. So for variations emerging from the regression, we are usually interested in sum of squares of regression. And the degrees of freedom are denoted by K, and the mean square is as computed. So Then the error is usually a source of variation, and then the total variation, which basically will be the summation of those columns. I have produced this, sorry, equation 1.35 will help us get the regression sum of squares. And I have produced that into this worked example. And from this worked example, we can decipher some information that one, the F ratio is 123.147. That is important for us. And then we have 4 degrees of freedom. So when we set the alpha at 0.05 to test the hypothesis that beta sub naught is equal to 0, then the F statistics produced from the table will be 10.13. But the computed value is 123.147. So clearly, from our estimate, we can reject the null hypothesis and conclude that at 95% confidence that advertising has an explanatory power. I wish to note that the F statistic usually helps us to see the overall model fit. And so our model needs to be statistically significant for us to say that we have produced a model that fits the data well. Let me pause at this level so that we can engage. Joyce?
Thank you so much, Daktari. I don't think we have ever had such an elaborate explanation of regression analysis, and we really appreciate you for preparing the slides and taking us through step by step. So I'm seeing quite a number of questions in the chat, and I hope we can reach at least, most of them. So I'm just scrolling up and I'm checking. We still have even more people joining. And please, if you have a question or comment, be sure to type it in the chat so that we can capture that. If we don't capture it today, it will definitely be addressed. So Renson Wanyonyi asks, good morning. My question is, when using regression, either linear or multiple, how many model estimates should be made, such as line of best fit, multicollinearity, and autocorrelation, etc.?
Good. So how many
models?
How many models? Huh? Okay, I get your point.
Do I continue with the other questions, or do you want to take that one first?
You can maybe raise 3, then I try.
Okay, Fatsuma Ali had asked a question. I'm just trying to get to it on the chat in the order they were asked. And Fatsuma, I'm not sure if your question was already addressed. If it was, let me know. And I think you had asked something around, sorry, I'm just trying to get there. They're coming fast and furious. Give me a minute. Lina also asked, I don't know if you address this. Lina also asked, my concern would be how to introduce moderating and mediating variable in regression equation. And then Ruth Odhiambo asked, is it a must? I think you already answered whether it's a must to have these moderating or intervening variables. You said it's not a must, but Lina also had asked, how do we introduce moderating and mediating variables in the regression equation? I think you captured that in your explanation, Daktari. So I think that one is answered, yes. And then Ernest Kirui asks, Daktari, kindly clarify on the difference in the types of the outcome or response variables between linear and logistic regression and the assumptions that must hold true for each to apply.
I think let's address that. And not forgetting Renson Wanyonyi's question about how many models do we estimate. Well, for the data set and for your objective, you will fit a single model. But the question you're asking about autocorrelation, multicollinearity will be the diagnostics for that model. And some of those have been captured in my subsequent discussion on multiple regression. And so probably when we have that engagement, we can see how autocorrelation is handled. And I've actually have mentioned issues about autocorrelation as well as multicollinearity. So you set, based on your objective, a single model, but you want to establish that the model is robust, it is sound theoretically, it doesn't have issues that would be problematic. And I think that should also help us when we read papers. We need to read papers and get the gist thereof, but run very fast to the modeling issues and ask ourselves whether the authors have done a good job in producing a good output and their confidence thereof in the output. Allow me
Wonderful.
now to address Kirui.
Yes.
Yes, is raised a good question. The outcome variables and then the types of regressions. I think I got it right.
Yes.
Now, in the case we have displayed, that is Aila Enterprises, the outcome variable is continuous. You see sales. When you don't sell at all, you report in your books 0 sales. So it's got a true origin. And then you can sell until everybody knows you're the most valuable company in terms of sales. So we have extremes. Now, in my preparation, I have the case for for the case of continuous variables being the outcome variable. But I also had made a preparation for what I call models of qualitative choice. I remember when we were discussing with Aurelia, I said that I will be interested to engage on that note where we think of models of qualitative choice. And so that's where Kirui is asking a question. One, I think let me just flip there so that you see. So the question, you've seen that some of those things that Renson answers are already planned. So I am here, models of qualitative choice. Here is a scenario where we are thinking of the response may not necessarily be continuous. It is dependent, I mean, it's a variable that is qualitative or categorical, and we do what? We use it as a response. So one question is to use a dummy dependent variable. And you can see in this case on page 60, we are proposing the dependent variable to be dichotomous. And Joyce, I used this example earlier, but it's here already.
Yes.
Y is equal to 1 if a person is attending this webinar, and 0 otherwise. So maybe for my students, when I meet them, I might give them a question and I will be checking whether they attended or not.
Yes. Okay.
So the variable is a dummy. And the other question might be whether the person attending this webinar is at home or otherwise. So maybe if I'd ask how many of us are at home, how many of us are in the office, and the like. Anyway, so we can use a dummy dependent variable. So I'm answering to read. The alternatives might be to see what other models might exist. And so I think I have mentioned 4. There could be others. One of them is linear probability model. And now linear probability model uses ordinary least squares. And as I mentioned earlier, we can also use others like the maximum likelihood method to estimate, or the method of moment. But we can also use the probit model, which uses cumulative density function. Basically, what happens, we transform the values into a normal distribution and get z-scores and compute. And the third one is using the logit model. And here we use logistic distribution functions. So you remember earlier on, I say that some function is used, and a colleague asked which kind of function. So I'm trying to unpack those functions here. So you can use the logistic distribution function. And then TOBIT, the TOBIT model, sometimes called the censored normal regression model. Basically, it is an extended probit model that now uses, we can either censor the normal regression model, or we can truncate the values. A good example can be our sales example. When collecting data from organizations, because they may not be interested in giving you actual sales value, we may use ranges that your sales is ranging from, say, 0 to if they're in thousands, or say if they're in millions, 0 to 10. So you'll have many small businesses falling between 0 and 10 million shillings in an annual period. So if you capture a lot of data with such kind of information, you see, we will have one response when somebody says the sales is falling in between the range of 0 to 10, 0 shillings to 10 million shillings. But see, how many businesses may be falling there? And what is the actual value? Maybe no business recorded 0 sales, sales worth 0 shillings, but there are many who will be into 1 million, 2 million, 3 million, 4 million. Let's look at the next graduation. You may say from 10 to 20 million. So from 10 to 20, 30, 20 to 30, moving to the extreme end. Assume your range is a business that is having about 100 million of sales per annum. So there's a likelihood that you'll say above 100 million. When you say above 100 million, you're also having people who might have billions of shillings of sales included if they're in your data set. So you're saying that many times when we truncate values, or when we censor values, we may not be producing outcomes that are realistic. And so we may not use the ordinary least squares to estimate such models. And I was going to show you from my thesis using binary logic model to show that, yes, these outcome variables can be qualitative in nature, and that's why we call them models of qualitative choice. And so we can proceed in that direction at the appropriate time. Does it answer?
I hope you are well answered. All right. I know we are going over time, but there's a very high interest. So I think we will just choose to stay here the whole day.
I can allow you up to maybe the next 7 minutes, then we wrap up.
Okay, thank you so much, Dr. So Fatima Ali Fatsuma asks, when and where are we supposed to use the different regression analysis models? So that's a general question. And we also have a few other general questions. George Wawero asks, oh no, this one is a quite specific one. George Wawero asks, at what instances do we use n-1? The workings here have used n. And then Dr. Tony Uwandu Uzoma says, what is the significance or implication of intercept? What is the implication if the slope starts from 0 and when it doesn't start from 0? I think he was also asking in line with Mike's question, must it start from 0? So I think you can take those 3, and I'll check the chats for more.
Thank you. When and where?
To use the different regression models. So Fatsuma Ali would like to know.
Okay. The starting point is to ask ourselves, are we estimating this model assuming that the relationship is linear? Because then that question might be using multiple or simple linear regression, or is the relationship likely to be curvilinear? That means we use polynomials. So we need to sometimes fit into the data and see, Again, where do we situate ourselves with our research? Are we proposing this when we already have data, or we're proposing when you're going to collect data? So those are questions that we may want to ask ourselves. But if the outcome variable is not continuous, then we need to look at the class where we can use models of qualitative choice or dummy variables. Again, sometimes we have dummy variables as explanatory variables. For instance, using sex or gender. I don't know which one is which. So let's use sex because it's a bit straightforward. Male, female. Though, of course, today you find that question has many multiple answers. So if you're traditional, like me, you use sex to mean male or female as an explanatory variable. We can fit it in as a dummy variable where you have 0, 1, and the like. Now, I think earlier on, I displayed n minus 1. This table, the generalized ANOVA table, shows us that we're looking at n minus 1. And this is for multiple regression. I don't know whether that table helps answer Waweru. And then the other question on the significance of the intercept. The intercept is basically the line at the point at which the fitted regression line intercepts the y-axis. Its significance will be in our explanation, given the data that you are looking at, because it tells us what happens without fitting the model, basically what is called the null model. And for the logistic regression, for instance, when we explain it, we'll be seeing how the explanation of the variables you've chosen is different from the null. And so the intercept basically tells us the relationship that exists between these variables when the explanatory variable is 0. And that's basically the question that we usually ask ourselves in the test statistics. You see, the hypothesis that we set many times were beta I, when it is 0, that basically tells us that the intercept must be the one that is playing. In other words, before this lecture, for instance, a number of
mute your audio. Proceed, Dr.
Yes, I'm saying that, for instance, before this lecture, a number of us had interest in regression analysis, and we had some knowledge. Agreed? So that will be what we had before the lecture. And if the lecture has happened, has it improved or diminished our knowledge? So that will be the explanation that we're giving based on this webinar. I don't know whether my example, though crude, makes sense.
I hope you were well answered. George Wawero. All right. So, Daktari, there are so many comments here saying, thank you so much. This was an insightful presentation. Ruth Odhiambo says, this was a good presentation. I look forward to more trainings. I'm also using regression in my study. I hope to understand better before I defend my work. So people are asking for more. And Janet Surum is saying, great presentation, Dr. Aila. You have simplified multiple regression for me. I am using it in my study. And
great.
Then, yes, we have quite a number of people saying, thank you, please share the content. We will do that. Charles Wakaya says, hi, Daktari, really loved the session. Can you loosely differentiate regression from SEM? Are they the same, or where do they pair or differ? So that's a question from SEM.
Or SEM?
SEM, yes.
That is, it's structural equation modeling.
Okay.
Now that is going deeper and deeper.
That is an advanced question, not for today's webinar. So I see we are
Yeah.
going to invite you again for another, we need a series, and this has been a demand topic on regression. So we really appreciate your time and you are able to do this. As you people know, in Journal Club, members invite guest speakers free of charge to give knowledge and to share together. And so we are really honored to have you here, Dr. Roskiru says, insightful session, Dr. Aila, regression made clear. Somebody even says, I have filled the online form. It's very insightful. So please fill the feedback form. This is very important to us. We check every feedback and we will be improving every time we get your comments. And of course, we'll send you the recording as we proceed. Oduor says, Odur Juma Paul, good and relevant presentation. I request for more of such classes, considering that this is mathematical and very applicable. Mildred Wanyama says, I am getting somewhere. I'm greatly helped. Fatsuma Ali says, it's really interesting. Thanks so much. And Carolina Mbogo, thanks for the presentation. Emmanuel Chikalipa, thank you, informative and insightful. Frank Corinda says, wonderful presentation. Agnes Sansa, thanks so much, Dr. So Oduor has a question. Please, Doc, which one is appropriate for a relationship-related study? So I think that's related to the earlier question, which one do you use? We're more general, and the discourse will continue. Dr. I don't know if you had any other pending question that you were going to answer as we wrap up.
Well, I don't have any. I'm just displaying my acknowledgement. I think now I'll include you here because you are such a wonderful moderator. Joyce.
Thank you so much. I appreciate it, Dr. And as we promised, we will be sending the information, the recordings and the webinar materials. So please fill in this form as we finish. And now, as we conclude, if you are able to switch on your video, please do so. And I will ask our knowledge manager, David, to take a gallery screenshot. So as we are putting on our videos, whoever can do that, I'd also like to acknowledge Aurelia Munene, who is the founder. Dr. I think some people will be asking for your emails. I know because our members are very highly engaged. And so if you can share, if you don't mind, or if you would like us to take all the questions and package them and so that you answer them, that's still okay. We can do that. We can liaise.
Yes,
there are many more questions.
You can pack them together.
Oh, okay, all right.
Yeah, but I'll also share my email.
Okay, thank you so much. So feel free to reach Dr. Some of you are asking for more, and we have promised to ask him again. We hope he'll say yes. So his email address is faila@maseno.ac.ke. So I hope you got that. Kindly switch on your videos if you can, and let's take a gallery screenshot. David, are you ready?
Hello. Yeah.
Hello. Wonderful. So I think we are on many pages on the Zoom, so you can start. We are smiling. And thank you all. Thank you all for being here. It's been amazing.
Thank you.
Yes, we will be planning a series of the same. I see even just regression analysis alone has generated quite a great discourse.
Sure,
yes, and we would like some people asking more general questions on quantitative analysis, which are not even in the topic. Some have gone ahead to the advanced deep regression analysis. So I really appreciate you all for your questions. If you're not answered, please rest assured you will be answered as we go along. So this is not the end of the conversation. John Kirare says, thank you, Dr. for the presentation. So David, tell us when you're done. @gmail.com says, thank you so much, Dr. for sharing your intellect. Jenny, wow, thank you so much. I appreciate you, Dr. and Wangari too for moderating. Thanks, Jenny. At Journal Club, our principle is sharing and learning. So if any of you would like to also host a research mentorship session on anything research related, whether it's in your field of study or in the field of research, please feel free to do so. You can book and also
Thank you for
present.
sharing your photos.
Oh, wonderful. David, I see you are done with the photos. Oh, thank you so much. I appreciate you. Okay. So on that note, everyone, I'd like to say have a good day. Those of you who will be doing Shut Up and Write, please let us know. I know some of you are not yet our members, so please join on the link. If you're not yet in Journal Club, we usually take 2 hours every week to do individual study so that we can apply these things practically in our work. So we still have more chats coming in. Everyone, it's been amazing, and goodbye. You can leave at your pleasure. You can unmute and say goodbye if you like. Okay, thank you.
Thank you.